Okay, now I would like to add some few notes, and I hope this can help you for further studying the mechanism of materials for finals preparation. Okay. So let's see these numbers. Problem 6, 4, 12. So you need to plot the shear diagram and the moment diagram for the beam AC, as we can see in this figure. This is the problem 6 to 13. I also attached the same problem into your exercise so you could check those questions. So to start with this problem, as usual, we are going to make the free body diagram. So you could start, if you haven't checked the problems, you could try the problem and then see which steps that you still have probably not really sure how you are doing that. So let me make it smaller. Okay. And then let me make a Freebody diagram. Okay, so this is A. Let me write A, and let's say this is B, and then this is C. Should be B should be a little bit here. Okay, and then we have the triangle for the load distributions, and then this will be 40 kilonewton per meter, and then we have uh, that part 40 kilonewton, the external forces that is on point B. So as we can see from the picture that I believe this will have the external reaction here. Let's name this Cy, and then we have a moment here because it's fixed on the end of C, right? So moment C. Okay, and then what else do we have? The distance, right? Distance here. This is 2 meter, and then this will be 3 meters. Okay. Okay, the distribution load, we can simplify it. So for the triangle, so you have the distance 2 meter, the base is 2 meter, the height is 40. Okay, so this will be 80 but divided by 2. So we have here, right? Let me write half multiplied by 40 by 2. So this is 40 kilonewton. And this will be 1 over 3 of 2, right? Or 2 over 3. So this will be 4 over 3. This will be 2 over 3. Okay. Okay. I think we get all uh, set up. Then first we can take the statics. So take the first is the Fy. We get negative 40 plus 40 and then plus Cy. So we could just simply say that since so this is Cy equal to 0, right? Okay. And then take the moment, and then let's say we take it in C, on C. So this is equal to 0. Okay, so so 40 by 3. Okay, and then another 40. So let's say this is, let me just make it clear, this is positive over there. So 40 and then negative 40. So 2 over 3. 2 over 3 plus 3. 2 over 3 plus 3. Or 11 over 3. right? And then minus MC is 0. So we can take that. So 40. So this will be MC is negative 80/3 kilonewton per meter. Okay, and then we could take the segments AB. Okay, we could observe this segment. So observe AB, that is, we are going to take it between this. Okay, so let's say okay, let's say that's A. So let's say this is A and trap X. Okay, so we are going to get V1 and M1. Okay, let's say this is in function of X. I'm going to take it into our functions now. So let's say this is X distance, or let me just write this is maybe small a to distinguish between A and X. Okay. And then what do we have? On this side we have distribution load, right? Okay. And then what else? Okay. Oh yeah. And then we take so if we take the ratio, so for example for this one, the triangle is 42, right? And then we have here, we have X and let's say Y. Okay, so Y over X is equal 40/2. So Y is 20X. Okay, so this will be 20X. Okay, by the ratio of these two triangles, right? Okay, kilonewton per meter. Okay, now from this part, we could also take the resultant of these loads, which is probably around here, that this will be 2/3x, right? And this will be 20 by x and then divided by 2, so 10x and then x squared, right? Let me write it in the green, 10x squared. Okay. And then using the same static, let me just erase this part here. So let's take the Fy equals 0. So we have V1x plus 10x squared is 0. So the function is just a parabola. Okay, just a parabola 10x squared or minus 10x squared, sorry. And then the moment with respect to A, and I think I would just make that part positive. So this is equal 0. So negative or 10x squared 1/3x plus m1x is equal 0. So m1x, this system, the function is negative 10/3x cubed. So we have all the equation we need, I think. If you want, you could also try to make out the BC segments. The way you do it is taking the segments from A to maybe here. Okay, so this A, B, and then this is probably like small b like that. And then we can make simply say that we have this is 2, this, let's say this is x. This is x, this is 2, right? And then you can start the same direction from what we have in AB, and you could describe another function that is going to be here, which is you have v2, and then you have m2, and then you could define these functions here that will going to define your functions on your diagram, okay, in shear and in moment. Okay, you could do that, but I think to simplify our process, I will skip this and then just let's take a look what will we have in the whole diagram. Okay. Okay, now we can take the diagram. Let me put the whole graph. Okay. Okay. And then let's simply take the axis. So the first one here is our V. So this will be V. This will be X in meter. So first we have the V equal this one. Okay, let me and this one for the moment. So for V, for the shear diagram, we have negative 10 x squared. So this will be just a normal parabolic. I think we can simply note the significance distance, that is 2 meter, and then 3 meters here. So let me just write that. I think I will just move the axis a little bit up here because I believe we are going to have a negative value, right? So we are going to take it. So at x equal 2, it's supposed to be at point B, right? So we can take this at x equal 2. So V2 is equal negative 40. So we could take that into negative 40, probably around here. Let's say this is negative 40. So this is 20, this is 0. Okay. I think not really good, maybe like that. I think not really parabola. I think this way better. Okay, I think this way is better. Okay, so we have this. Okay, and then at the same time, at the same distance too, we get our resultant or our external force 40 kilonewton. So negative 40 and then push up a little bit. So it goes way here, take it into 0, right? So into 0. So we get 0 for the V. And then what else? And then because nothing happens in BC, there is no external force. So we can assume that all the way here will be 0. So this is your shear diagram. Okay, similarly, we could take this and then maybe take it over there. And then just keep in mind that the moment is the integral of the shear. So we are going to take this into another equation here, which is m1x negative 10 over 3 x cubed. Now we have a cubic formula. Okay, So what will be for this cubic is perhaps we could take as similar distance for x equal to. So we can take, this will be 80 over 3, right? Negative 80 over 3, which is around almost 30, so 20 something, right? 20 something, 26, around 26. So if this is perhaps 20 here, 30 here, perhaps that is going to be here. And then it's cubic, so it must be a little bit steeper like that. Okay, perhaps that's our, so this will be negative 80 over 3. This is the m. X is x. This is kilo Newton meter. This is kilo Newton. Okay. Okay, what's next? Next is basically in V is a constant, right? It's a constant. So we could check what's happened here. Or if you would like, you could always taking into the segment BC if you want. But you will get the same same results. So this will be that. Okay. Just to be safe, I think I can give you how to get the other segments here. Let me just write additional observe BC. So BC we can take Freebody diagram and taking into, and this is, I think I can make it a little bit smaller. This is A, this is B, and let's say this is B, okay. And then let's say if this is 2 meter, we define the x as the A, the whole thing here. So this part here will be x minus 2, okay, meter. And then same thing here, load distributions all the same. So this will be 40 kilonewton over there. Reaction, this is 40 kilonewton. And then the same as the original source, this is the 4 over 3 meter. And then what we are going to do is we are going to define the M2, oh sorry, V2, this is V2. And then the M2. So we can take Fy equals 0. 40 minus 40, or let me just write V1 or V2 plus 40 equal 40. So V2 is 0. Okay, as we can see from this part here, 0, right? And then sigma m at B equals 0. So that will be, let me define this, positive. Okay. So 40 and then 2/3 plus x minus 2 minus 40 plus m2. And then we can solve this. So this will be negative 2/3 plus x. Or maybe this factor it. That's this factor. Okay. So this will be cancelled. And this will be cancelled, right? So basically, m2 is negative 80/3, which is this a constant, as we predict from our assumption here, just a constant. Okay. And that's it for 6.4.12. Okay. Okay, this is additional video for the mechanics of materials. So this is one of my. Okay, so first we draw the Freebody diagram. Let me just draw that. Name all the points. And then perhaps this is B, this is C, and D, and E. Okay. So let's describe all the forces. And then what else? We have to support, right? To support. Let's name this AY and then the Y. Right? And then we have all the distance we need from the picture. This one 1.5 meter. And then what else? This one. Okay. This one is 1 meter. And this one is 0.5 meter. And then the last one is this. This is 1.5 meter. Okay. Okay, so we take the statics first. We compute the sigma F and sigma M. Let me just take from a moment first. So take moment, let's say taking D. So we are getting the AY. So let's take this equal to 0. And let's make the this part as positive. So we take that negative AY multiply with 3 meter, right? And then plus 10 kilonewton multiply with 1.5 meter, and then minus 6 kilonewton multiply with 1.5 meter equaling to 0. Okay, so yet this is going to be so negative, so AY or 3AY equal to 15 kilonewton meter minus 9 kilonewton meter. AY is This is 6 divided by 3, so this will be 2 kilonewton. So what else do we need? The sigma f. Okay. So sigma f y, this will be ay plus dy minus 10 kilonewton minus 6 kilonewton equal to 0. Ay is 2, so 2, so we can write, or we can simply write dy equal 16 minus 2 is 14 kilonewton. Okay. Okay, and then we slice up the segment because we want to determine the flexural stress at C. So we are going to perhaps slicing this part here. Okay, so slice that part. So we are going to have, so A, B, let's say C is around here, hit that point. So we are going to have VZ and MC, right? So all the things we need, we already arrange in our graphs. So take this as 2 kilonewton, and here is we have 10 kilonewton, and then we have what? Yeah, I think we have all needed. So yeah, this part is 1.5. This one here is 1 meter. Right? Or maybe we could just make this part here is exactly at 1 meter. So let's just make this easier to solve. So we can take the moment at C equals 0. So we can take that and make that this part is positive. So minus 2 kilonewton multiply with 2.5 and then plus 10. And then plus the MC is equal to 0. So MC is equal, negative 5 plus 10 is 5, so it's 5. Okay, I think we get this M, and then what's next is we take the inertia, find inertia from here. So the inertia will get this pH cubed divided by 12 minus, or it's equal, sorry, it's 100 millimeter, and then multiply with 200 millimeter, and then cube, and then divide by 12. This is around 66.67 million, and then millimeter with power of 4. So, okay. So for the first question, it's asking the flexural stress distribution. So we could write down flexural stress distribution. So sigma. So what should be This should be distributions. So distributions at x equal 2.5, right? So at this point C, so this is 2.5 meter, right? So this is the one that we are going to evaluate, the section C, right? Okay. So we could note the x is 2.5 and based on y, right? And remember that y, according to this picture, y will be in millimeter. Okay, so this will be equal to negative mcy divided by the inertia. Okay. Oh, this is negative 5. Sorry, negative 5. So it should be opposite sides. Okay. So we are going to incorporate this m, which is negative 5 kilometer meter, and then this is 1. This is the inertia. Inertia is 66.67. This is in millimeter to the power of 4. So we are going to um, calculate this. We are going to make into Newton over millimeter squared or MPa. So we are going um, to take the 5,000. So 5,000, 5 million. So 5 millions. So 5. Let me check with my calculator first to make sure that we have a correct answer. Yeah, I got so kilo here, and the meter we go to millimeters, so it's going to be millions. So we'll be canceling with this, right? Let me just okay, so divide this too, so we get 0.074, or let me just simplify to 5, and we still have y. Okay, we still have y. Okay, I think taking this into our uh, calculation, or if you would like to take y here, I guess the y will be in this middle part here, right? So you could see that y will be taking 100 millimeter, so we can take at y 100 millimeter. We can uh, further compute this and multiply with. So 100 millimeter, we can multiply with, divide by 1000, it goes 0.1, right? So we multiply with 0.1, and we can just add the number, or MPa, like that. Okay. Okay, and then we take this sketch for number B, make two-dimensional sketch for the stress distribution. So we could make that. So basically, we are taking this. We have to. So this is the middle part. So this is 100 millimeter. Let me write clearly. Okay, and that's 100 millimeter. So this will be stress distribution will be like that. Okay. Okay. So the maximum is 100 millimeter multiplied with our uh, calculation here. Oh, I think I get it wrong here. So I think we just multiply with 100 because it's already in millimeter. So this is to 7.5 MPa. So this will be 7.5 MPa, and this will be what, 7.5 MPa, okay, at the 100 meter, right? Okay, so this is for number B. For number C, determine the total compressive force. Total compressive force. So total compressive force. This is going to be equal to compressive average magnitude multiply with 100 millimeter squared. So taking this and calculate the average, we are getting these two numbers. So we are getting divide by 2 because we have these two. So we get 7.5 MPa divided by 2 and multiply with 100 millimeter squared. Okay, going to be 3 37.5 kilonewton. Okay, this is the total compressive force. So basic total compressive force is, if you're confused what happens here, this is basically we take the sigma F over A, and then what this means is we are going to slice this samples become two squared. Okay, become two squared. One is having this maximum stress. This is also maximum stress. Okay, so we are taking all into this computation here. Okay. Okay, that's the number 7316. Okay. Okay, another additional content that is, I believe this is also in the exercise. So we have 743. Okay. So we have this picture here, the supported beam subjected to load of 200 kilonewton. And then we have the distribution load 40 kilonewton over meter for the segment AB. We have the allowable stress, which is 150 MPa. And then after some calculation, we need to select which design for wide plane steel from this table, Appendix D, from the Appendix D, that might be used for this application. I will provide the table. So because I'm using um, different unit in the textbook, so I'm using, actually this is D2. Okay, so this is D2. Okay, so we finish. We are going to select, depends on what this design has. We are going to select which one, okay, which one of the options that are available, and then we can select that as our choice. Okay, so first we are going to compute first, compute all the information needed. So firstly, as usual, we are going to know what will be the reaction here and here, right? So let's say we are going to observe in statics. Okay, let's draw A, B, and C. And what else do we need? Okay, I think we can just simplify. This will be AY. This will be P. And then we have here is W. W is 40. But I think we can just take it into here and make it WL over 2, right? This is L over 2. So we could take that right here. And then what else we have? Oh, we have reaction here, which is this is having a we can move this, right? So we can have this cy also. And then as usual, taking into the sigma moment. So L, and the write L is 4, W is 40. And then this will be all is half L. This is half L or 2 meter, 2 meter. And then this will be 1 meter. Okay, we take the moment. Take the moment at C equals 0. And then take this one positive. Okay, so AY is 4 meter. And then minus let me compute first. 40, 4 to 80, right? 80 kilonewton. So that part is 80. So 80 kilonewton, and then multiply by 3, and then minus P is 200, so this will be 200. So 200 and then 2 equal to 0. And then we can take 2, become 40, and then take 2 become 20, take 2 become 100. So 60 is 160, so AY is 160 kilonewton. I think we can take sigma F. So 160 plus CY is equal 80 plus 200. So this will be CY is 120. Okay. And then we are going to draw the diagram. So let me put another diagram here. Let's crop this first. Make it a little bit small. And then make a... I will draw directly. If you want to follow step by step, you can go back to the chapter 6 to see how we get the diagram. Okay. So let's say this is the L over 2. This is another L over 2. Okay. And then what else? We get the first is AY is 160. So 160, perhaps that is going to be here. So this is V. This is X in meter. This is in kilonewton. So this is 160. And then according to what we have, it's supposed to be going down, right? It's supposed to be going down. So it's taking this negative slope, but it's linear. So it's supposed to be like that, okay? And then to get a more constant P. Constant P is 200, so Or I think I can show you how. Let me just erase this part first. And then simply taking the segment AB. So segment AB, in which we are going to define that this will be in between 0 and 2. And then we name this A small a. This is X. Let me make a better beam. Okay. And then this will be A and then A, right? We have moment and shear. Okay, that's difference. And what we have, this is, so basically we are going to slice up until there. Okay. So this will be still this is W, and this is X. So yeah, we can just write that Vx or writing the sigma f is taking this is ay is ay minus va and then minus the wx, which is here, this one, and this one here is wx over 2. This is equal to 0. So va or vax, this will be equal, ay is 160 minus 40x. Okay, this is the linear equation. So uh, at x equal 2, we have this is going to be 80. So we get this is going to be, this is 80, right? And then 80, we get pushed by p equal to 100, so we get 200. So this will be, let's say this is so this is going to be 200 kilonewton from the 80. So we get around at this point here, it will be negative 120 kilonewton, right? So that will be our shear diagram, and then nothing happens until C, it's a constant. And then at the C, we get a Cy, which is 120, right? So we get back to Cy here. This is another 120. Okay. So this will be our diagram, shear diagram. Okay. Okay, and then for the moment, we are going to imagine, remember that the shear is the derivative of the moment. So we are going to, let's say, integrate. So this is positive, right? The slope is positive from A to B. Slope is positive, so it goes to be going up. It's supposed to be going up. And then after that, we are going to have a negative slope, but a constant. So we are going to have a linear equation. But we need to know the maximum moment, right? So we can get through our segment here. Okay, we haven't finished yet this part. So we take the moment at A equal to 0. So AY, let's say we take that as a positive. So AY multiply with X. Okay. And then minus WX multiply with X over 2. And then negative MA equal to 0. So MAX is equal, this is 160x, so negative 20x squared. Or you could integrate this. You could integrate it with respect to the x if you want. It's MAX. I think it's faster if you just integrate it. If you want to completely take the moment, you can do both ways. You can take the moment here from the sigma moment, or just integrate this. Okay, both are correct. Okay. So we are going to have a quadratic equation. So we can take this. If we take at x equal 2, we get. Let me compute first. It's 240. So 240 will be going to be, perhaps this is a little bit down here. So let's say that this is 100, 200, maybe here, 240. That is when x equal 2. So our graph, let me write with the light blue. So it goes to that. And then after that, we are going to have just a linear equations up until this point. Okay, and then this will be our moment diagram. But this is not really what we want to find, right? So we are going to test this design with the stress, allowable stress, that is 150 megapascal. Okay, how do we do this? So from this part here, we know that the M max is at x equal to meter, which is at x equal to meter, and M max is 240 kilonewton meter, right? Now remember that in the last part of our lecture, I tell you that we have a new property that we call S. This is for design. This is equal the moment max divided by the sigma allowable. So we take this 240 divided by 150 Newton over millimeter squared. So we are going to rewrite all, and then perhaps we can get into millimeter from meter. So this will be 240 million and divide 150. So this is Newton millimeter, and then this is Newton over millimeter squared. So we get millimeter cube, right? So we take this and calculate. This is going to be 1600 millimeter cube. Okay, so what will be the consequences? So if we have this S, so this S is going to be, so remember our S is we write here S is 1,600 thousands, right? Okay, we can take that and see for some part. So what we are going to find is the S. Okay, the lightest. So this S. See, we have S. Okay, for XX or YY, we have those S, right? So for the S, that is 1,600. We have, wait. Going to find bigger than 1,600, but yeah, I think bigger than that. So I think this one here. Okay. So this is going to be this. So it's going to be, so it reads that this one means that 610 and 92. Okay. So according to the table, so the lightest W section beam is for this design that S is to 140,000 millimeter cube. So if we take with this, if this is our S, then our M max, okay, or I mean, this will be the maximum stress will be the M max divided by the S. So the 240 divided by 2140. So let's compute that. So it's going to be around 112.1 MPa. Okay, this is kilonewton meter. This is in millimeter cube. So we are going to change to this is multiplied with millions, right? So this will be 10,000, right? So this is I think quite logic because 112. So 112 is lower than the 150. That is in our design wise, it's lower than our allowable stress. So the design is I think quite good. Okay. Okay, that's the number 743. Okay, I hope all the informations needed helpful for your preparations. Okay.